Welcome back, dear students. Having completed scheduling algorithms, today we are going to look at another concept under process management, which is deadlock. A system consists of a finite number of resources to be distributed among a number of competing processes, as we saw. The resources are partitioned into several types, each consisting of some number of identical instances. A process must request a resource before using it and must release the resource after using it. A process may request as many resources as it requires to carry out its task. The number of resources requested may not exceed the total number of resources available in the system. A process cannot request 3 printers if the system has only 2. That is, the maximum number of resources requested by a process cannot exceed the number available in the system. Now, consider the situation where there are two processes P1 and P2. P1 holds the resource R1 and requests the resource R2, which is held by P2. P2, on the other hand, holds the resource R2 and requests the resource R1, which is held by P1. None of these processes can release a resource it holds without getting the resource request. So it's just like two different children having two balls of the different colors, but they want the ball of the other one. But each of them says, before I give you my ball, I must have your own. In such a case, nobody will ever have the ball of the other one, and each will remain with the ball it possesses, as you can see. So you see that, as you can see in the key, the dash line represent request and the solid one represent allocation. So P1 is allocated R1 and request R2. P2 has R is allocated R2 and request R1. So you see that in this case, it forms a cycle which will never terminate, and this cycle is what we call a deadlock. None of the processes will be able to have access to the requested resource, and they will remain in a deadlock. A set of processes in a deadlock state. A set of processes is in a deadlock state if each process in the state is waiting for an event that can be caused by only another process in the set. That what we call deadlock. So for a set of processes to be in deadlock, each of the processes in the set must be waiting for an event that can be caused only by another process of the same set. That is, each member of the set of deadlock processes is waiting for a resource that can be released only by a deadlock process. None of the processes can run, none of them can release any resources, and none of them can be awake. That's what we call deadlock, as you can see in this cycle. So now, the resources may be physical, such as printer, hard disk drive, memory space, and CPU cycles, or logical, such as files, semaphores, monitors. These resources could either be a preemptible resources, that is one that can be taken away from the process with no ill effects. When we talk of no ill effects, talk about no disastrous effect on the process that was currently holding it. Or it can be a non-preemptible resource, that is one that cannot be taken away from processes without causing ill effect, e.g. CD resource. And when we talk of CD resource, imagine you are using the CPU to write data into a CD and you currently stop the process. It's going to have an ill effect on it, because if it's a CD that cannot be rewritable, then you have wasted that particular CD. Now, whereas for a memory, it can be preemptible, because a memory um, during a context switch, the memory can move to a particular process for execution before coming back to the process on which it has been removed. A process may utilize a resource in the following sequence. That is, it can either be a request. If the request cannot be granted immediately, then the process requesting the resource must wait until it can acquire the resource. Apart from request, we can have use, that is, the process can operate on the resources, or we have release, that is, the process releases the resource for to be used by another processes that is being doing the request. So when it comes to process and resources, a process has three different ways of using the resource: either through a request, that is, he wants the resource, using the resource itself, or either releasing the resource. Necessary condition for deadlock to occur. Kaufman, that is the person that identify that is about the origin of deadlock, Identify four conditions that must hold simultaneously for there to be a deadlock. So there are four conditions that must hold simultaneously for deadlock to occur. These conditions are mutual exclusion. A mutual exclusion means that what? A resource can be assigned to at most one process at a time. That is, there is no sharing. That will call mutual exclusion. If another process requires that resource, it must be delayed until the resource has been released. The other condition is hold and wait. That is, requesting process hold already. That is, requesting process hold already the resource while waiting for requested resources, as we can see here. So P1 is holding R1 and is requesting for R2. Same thing, P2 is holding R2 and requesting R1. The third condition is no preemption, meaning that what? Resources already allocated to a process cannot be preempted. That is, a resource can be released only voluntarily by the process holding it after that process has completed its task. But now, since no one wants to release, because for every process to complete execution, he needs the process he or she is requesting. And for it to allow the process it is holding, he needs to have the process requesting in such a way it leads to a deadlock. The last condition is a circular wait. Let us understand this particular condition because it is very important, this fourth one. There must be a chain of processes such that each member of the chain is waiting for a resource held by the next member of the chain. That is, there exists a set P0, P1, Pn of waiting processes such that P0 is waiting for a resource that is held by P1, P1 is waiting for a resource that is held by P2, and so on till Pn minus 1, which is waiting for a resource that is held by Pn, and Pn is waiting for a result that is held by P0. So we must have that circular chain. As you can see here, this is our circular chain, as you can see. So these four conditions together, if they hold simultaneously, then automatically there is deadlock. So we are going to end on deadlock for today because in the next video we are going to look at resource allocation graphs where there is some drawings which are needed and to be understood. And there are some tips because remember, being a member of the buy family, a lot of tips is given to you when it comes to such situation. So tips will be given to you on how to properly draw and analyze a resource allocation graph. We are going to have examples and as tradition stipulates, an exercise will be given at the end. So do not forget to like, to subscribe, and to share for our community to grow, dear members. And see you in the next lesson.